Hello, my friends. Welcome back. This is Dr. Mohammed Nizami again with another presentation. This is the second part about talking about the design of RF to RF crossover. Okay. Last time we have spoken about how we go about designing a. In the last video, you can click and watch that prior to this because it might be much better. That way you can have the complete story, I might say. But we are designing a RF to RF crossover using via transitions. This is embedded in the board. And eventually we take that design and make it into a chip, an actual chip that is similar to these guys, except now these guys are limited to 6 gigahertz, or this guy here from AVX, Corsica. That one we want to try to see if we could preserve the frequency response all the way through Ka band somehow. I know it's very difficult since as soon as you package this and you put it onto the board, there's a lot of issues that comes in. So that's why a lot of designers are basically, they design this into the board, they embed it into the board. So let's just skip over and resume where we have left last time. This is the stack layer that we have chosen. It's a 6-layer board made of Rogers 4350B as a core, and the pre-preg is Rogers 4450F, okay? And so we have decided we're not going to use blind vias, okay, because they're expensive and it involves processing. We're going to use back drilling, okay? So the first thing that we did, we showed how the back drilling, if we don't do back drilling and we leave the unused part of the stops from the via transitioning from the top of the board down to the strip line layer, we end up with a frequency response that could be undesired, where as soon as the additional unused part of the stop, which is open stop, is a quarter wavelength at some frequency, that particular frequency, it will be presented with short at this point, and you get a null in the signal. And this is the formula to predict that. Although I've tried many times really to use this formula, I've always came off, way off, not even close. And that tells you that there's more to it than just this. But so we have decided, okay, let's see, here's a transmission line. We put that together. We built the stack layer, okay? The yellowish 2 layers here are the pre-preg, while the cores, the 3 cores are right there. Okay, 1, 2, 3. And we've decided we're gonna use the top for microstrip. This is a ground layer. This is a ground layer. Bottom is for microstrip, and the middle is a third one. Layer 3 is the strip line layer, okay? And we have swept this line. The characteristics, the loss looks good. Everything looks good. And then we decided, okay, let's do a transition now from microstrip on top to using a via to the bottom, okay? And that's sideways. It looks like this with 3 vias on each side, 3 ground vias on each side. And we did that, and the return loss looks okay. Maybe you want to try to push it toward, like, say, minus 13 dB, but this is okay for us right now. So this works nicely and everything is fine. And then next we said, okay, let's build a transition that goes from top to the layer 3, which is a strip line layer, okay? And in this case, we've used the via as is without any back drilling, and this is what we end up with, as you can see. And this is what happens in here is the frequency response. This is insertion loss, and this is the return loss. And you can see the insertion loss, basically there's a null at 25 gigahertz. And and that's a problem, because not only problem here, but also because it started rolling off, affecting the frequencies. So this transition here is is not usable beyond, say, 6 gigahertz. Okay. So so and you can see that even the impact can be clearly seen when you look at the E field propagating down from the microstrip line down to the strip line, where the additional unused suction in here at 10 gigahertz, it was okay considering, you know, but at 25.4 gigahertz, which is the null frequency, that's this frequency here, you can see what happened is the signal doesn't propagate at all and just keeps reflecting back and forth here. So then after that, we said, okay, let's use back drilling. So we came in and we drilled part of the inner part of the copper of that via, and we lift out some of the rings because it doesn't really affect anything. In fact, you probably can choose a drill bit that drills the whole via, including the rings, but in my case, I excluded rings a little bit, and I lift off a fraction of a length here, just so that for safety, that I don't damage the line itself, okay? And of course, when you do that, you don't see anymore the roll off and the notch. You see even at 25.4 gigahertz, where the null was, the E field transmission really looks good. So now with that, so that means we are actually, let's turn over to here. So that's the transition right here. This is the first one without the, with the, let's highlight the main parts of this transition. Okay, and okay, so we're gonna, let's highlight the via. This is the transition right now. As you can see, what we have, let's do the one on top also, this one here. So we've got the transition right now. You can see that the via, let's look at sideways on this. You can see that this is the signal comes in on layer 1 and goes down to layer 3, while with the via in there intact, complete. Okay, and when you look at the frequency response of that, obviously you can see that the null frequency is at somewhere 24.5 gigahertz. Okay, let's see, 26, yes, 25.5 gigahertz. Okay, so which is unacceptable. So if you look at the E field on this, let's look at that. Now, let's look at sideways so we can see. Now, this one right now is let's see what frequency is this. This one is at 10 gigahertz, okay? So at 10 gigahertz, you can see that. Let's look at 25.4, the null frequency, and you can see that it is not propagating. So let's animate this. And for the heck of it, let's just see what happens. Okay, you can see the signal is going in, but it's not ever reaching over to the other side, okay? So now, well, if we change the frequency now, say another frequency where earlier than that, let's say 5 gigahertz. At 5 gigahertz, you can see that the signal reaches the other side easily, okay, without any issues, okay? Now again, if we again go to 24.5, which is where that the open stop becomes short, because as you know, quarter wavelength, a parallel open stop, if it's at the point that it's a quarter wavelength, it becomes short. As you know, the quarter wavelength transformer is an inverter actually. If the load is, if it's open, it's short, it looks short at the input. And you can see that right now. That's this here. So now let's do this. So we're gonna take the same design, and in this case, we are going to basically drill out the part in here and just keep the section, which we're just going to keep the section that basically, let me see if we could show that. As you can see, let me highlight the okay, so you can see now what I did is we drilled the open stop, we drilled it out, and now I still have some of the rings in there because the drill bit is smaller. It's just about the diameter equal to the diameter of the drill bit to the hole. And now let's see what happens. So if we do this, if we look at the frequency response, ta-da, basically we don't see any issues. Let's look at the animated E field and show the difference. Okay, so now let's animate this. I don't know what frequency is this. Okay, so at what frequency is that? Now you might know that, okay, so that's at 25.4. That's where the null basically was, okay? And so if we change that to say 10 gigahertz, we get similar response because flat to that point. Okay, so we're really not interested right now in a via transition from one side to the other side of from a microstrip line to strip line. What we're interested in now, let's take this now and put one back to back, and then that's basically where we can make a crossover using this. So let's do this first of all. Let's do a back to back, and that's one of the designs that I did. Okay, which is exactly the same transition was copied over, rotated 180 degrees. And if we do that, we end up with, let's see, this here. Let's just show the, okay, so we got this here, and we've got this, and then we've got the strip line. Okay, so you can see that right now we have these. I got the two vias, okay? And the vias are the drill hole vias, okay? So now that's basically, this is two of the design that we just did, the transition from microstrip to strip line. We just copied it over and back to back. So we're actually now, we're transitioning. Let me get rid of the, of this guy here. Okay, so now what we are in transitioning in is we transition from microstrip to strip line back to microstrip. So it's microstrip, strip, microstrip. Okay, and this works when we sweep it, it works fine. So let's look at the results of the sweep. Okay, so we're very much very nice, and I did check it earlier. The loss is in here, close to being double the loss of a single transition. So everything checks. Now we're ready to, at this moment now, what we need to do in order to make a transition out of this, oops, we're in the wrong one. Let me close this. So right now, if we want to make a transition out of this, I mean, a crossover, this by itself is a crossover right now. So you could use this in the board and just basically go down here and cross over with macro strip line on this one, and this one will be a tunnel that gets in the signal that is crossing this signal. And that's exactly what the next project is. So let's look at that. So, well, before we do that, I simplified it a little bit. So what I did is I reduced the number of vias. So this is another design, which very much it's the same thing. Let's go through it. So we've got the two microstrip lines, and then we got the the strip line, okay? Now, and we've got the vias in there, okay? And I had four, I put in 4 ground vias for EMI purposes on each side. So it's very simple, much simpler than the other one. It's still back drilled, okay? And so when we run this, we get exactly the same. Nothing has changed. I removed the copper that was on top, as you can see, just to simplify it, okay? So we're okay now. So now, finally, we're gonna go to the final design, which is this. So this is my final design. Now I have, this is a 4-port network now, where this one is a macro strip that crosses this way. This is one signal. And then another signal that comes in macro strip, but it's right at that point, it gets over and gets transferred to a strip line beneath. And that's basically what we have right now. Okay, so this is the design of an RF crossover on a 6-layer board, okay, using the technique of via transitioning from macro strip to strip line, okay? And if we run this, let's run this. So port 1 to 2, we still get the same exact response, while the other one, we get this one here, which is pretty nice. As you can see, very tiny loss because it's only a 3 mil line section. That's okay. So let's look at the E field now. Now the E field, as you can see, it's a 4-port network now. So let me take out the highlighting of. So right now what we have, let's look at it from top. This is what we have, okay? So this is macro strip. The one beneath it is strip line, and it goes over to here. And this is a macro strip. Now let's look at this sideways. As you can see right now, the signal comes in here, transitions with the, let me make these transparent so we don't have to see them. Okay, so the signal comes in here, goes down. Of course, these vias here, the vias here, as you can see, this is the via connecting the strip line on top. Let me put this one this way, this way. Okay, so we come in here, the signal comes in here, goes down. As you can see, there's a little tiny, there's a significant portion that is in these layers, and the strip line, and it goes in and then goes back up to macro strip, where the other one is orthogonally placed, and it's right there. So now one of the issues is to see the, let's see the isolation. This is the isolation, and it's also excellent. We're getting throughout anywhere between say a few gigahertz to 30 gigahertz. The worst case is M5, which is at minus 36 dB of isolation between the ports. So there you have it, ladies and gentlemen. So this is really, so let's animate this. This is an RF to RF crossover embedded on a 6-layer Rogers material board, 4350 and 4450. Okay, as you can see now, this shows you the complete signal transitioning. This is a 4-port crossover. So you can see that the signals don't interfere because there's now between this signal and the other signal, as you can see, there's a ground plane and there's another ground plane below, because the other one is a strip line sandwiched between 2 grounds. As you can see, this is ground, this is ground. Okay. Now, so and of course, if we check the impedances, we still got 48 ohms in here, and the other impedance is 48 ohms. So this is successful. Now let's take this further. So we're going to take this and we're going to take this, and that's for the next video, and make actually a little device out of this. So let's pretend that we want to, hopefully we don't want to compete with the with these guys, but let's say that we want to package it like these guys. Okay, there's no reason not to do so. So this is only 6 gigahertz, most of these guys. So let's I know that it won't be as cheap, but at least just for the sake of it, let's just try and do that. And basically so that's what we have here. We have a basically this one is still in the work. Okay, so what I'm going to do is we're going to create an input port in here so that you can actually, on the bottom, this is the bottom and this is the top. Okay, we're going to make a little, this is edge plated in here, a half via on the side that will serve as an input port to the one of the signals. Same thing in here, and we're going to do the same thing to the other one. And then I'm going to use these as ground vias. Okay, so these are the ground vias. There's 4 of them. Okay, and so tune in to the next video, and we will go through this from the start and see how this will do. Okay, ladies and gentlemen, I appreciate you are attending this presentation, and until next time, this is Dr. Mohammed Nizami. If you happen to be working for a company that needs any RF design work, please let me know. I contract out as an offshore outsourcing contractor designer. My rates are very reasonable, so reach me out at this phone number or at this email. Well, thank you very much, ladies and gentlemen. I hope you enjoyed this. So until next time, we'll see you. Have a great day.